Welcome, everyone. Thanks for joining us. We'll get started in just a few seconds. We want to give folks a few more seconds to arrive. Thanks for joining us, everyone. We're just going to wait a few more seconds for folks to join in. Thanks for being here to see warm ice. Okay, again, welcome. Thank you for joining us this evening for Warm Ice, How Alaska's Glaciers Are Responding to Climate Change with Dr. Bruce Molnia. I'm Crystal Gartner, your host, and I work with Alaska Endeavour. Before I introduce the moderator of tonight's event, I'd like to let you know that we are recording this webinar and it will be available on our website, alaskaendeavour.org, within a few days. Dr. Molnia's presentation will be about 35 minutes long, and we encourage you to type questions into the chat as you think of them, and we'll answer as many as we have time for at the end of Dr. Molnia's talk.
There we go. Can you see the screen clearly? Excellent. So I'll begin in just a second. I need to move some of these bars that are blocking a large part of my image here. Just a second, please. Okay, so to begin with, I want to give everybody a simple definition of a glacier, because we'll be using that term extensively during this next 30 minutes to 45 minutes. So a glacier is a large, typically more than a square kilometer, so about 4/10 of a square mile, perennial accumulation of ice, snow, rock, sediment, liquid water. They originate on land, move down slope under the influence of their own weight and gravity. They're formed by the metamorphism, the recrystallization of snow into crystalline glacier ice. And Alaska has about 27,000 glaciers with an area of more than 80,000 square kilometers. Only 700 or so of Alaska's glaciers have names. Not to be confused with an ice sheet. An ice sheet is a glacial land feature with an area exceeding 50,000 square kilometers, 20,000 square miles. And today, ice sheets cover most of Antarctica. There are two of them, the East and West Antarctic ice sheets, and Greenland. And during the Little Ice Age, ice sheets covered the same areas as today. There weren't any significant ones during the Little Ice Age. During the Pleistocene, period of time that ended about 15,000 years ago, a gigantic ice sheet covered Europe. Another one, several of them, in fact, covered North America, and South America also had ice sheets in several places. So what's important is when you have ice sheets on land, you've taken huge amounts of water out of the ocean, and it's frozen as ice in these ice sheets. And so global sea level goes down significantly. During the Pleistocene, global sea level was down more than 100 meters. In fact, it was more than 400 feet places. So continental shelves were far larger than they are today. And between 20,000 or so years ago and about 6,000 years ago, all of the major Pleistocene ice sheets melted away and sea level rose to a level comparable to where we are today. This is a valley glacier. This is an unnamed valley glacier in the Chugach Mountains. I put this picture in here because it shows almost all the important features that we'll mention throughout this presentation. This is the terminus of the glacier. You can see my cursor down here. These stripes are moraines. What's important in this particular picture, the moraines are elevated over the surface of the melting ice because it's melting so rapidly, and the sediment here is insulating the ice below it and causing it to melt at a slower rate.
Bruce?
On the side of the valley, there are
Bruce,
moraines.
I'm sorry to interrupt. Can you, is there something, maybe we're hearing a little bit of static on your voice. Is the microphone covered or is everything?
The microphone is built into the computer screen.
Okay. Okay, sorry to interrupt. We can hear you. It was just a little fuzzy, so wanted to check.
Sorry about that. But I was pointing out the lateral moraines here. And in this case, they tower 30 or 40 meters above the height of the surface of the ice, again, indicating the rapidity that this glacier is melting. As Bill mentioned, I have a number of publications about glaciers. Most of them are focused on Alaska. The middle one on the bottom is that massive, as he described it, treatise on Alaskan glacier behavior. So let's talk about the two important climate change related aspects that are directly glacier dependent, or in one case, the glacier dependent in one significantly influencing the glaciers. These are temperature and, as I mentioned, the volume of water that is either tied up in ice or it goes into the oceans. So on the left-hand side is a screen showing temperature from 1950 on the very left. This is global average, surface temperature, to the star, which represents where we are in 2022. And what you see in orange and blue-purple are two different scenarios of what might happen with warming continuing at rates, either what we're experiencing now or even greater warming than we've experienced over the last 50 or so years. And so the direct result of this warming is, you move to the graph on the right, here we are, sea level rise elevation today, and you can see this cone that represents different alternatives of what might happen. The measurements here are in millimeters, so 400 millimeters is a little bit more than a foot. And so we're looking at, in the next 60 years plus or minus, or 80 years plus or minus, potential for sea level rise to be more than several feet or potentially less than a foot. At the rate we're going, it will most likely be significantly more than a foot. This diagram shows temperatures in the United States, and you can see in blue, there's some areas that actually have cooled slightly, but the majority of the United States, including Alaska, is significantly warmer than it's been, gradually increasing through about the 1950s, and then warming more rapidly since then. Alaska is unique. It's warming more than twice as fast as the rest of the United States. And in Alaska, we have 19 first order weather stations, and you can see them in red here on this map. They're throughout the state. In the 71 years that they have existed, you can see individual seasonal temperature changes at 19 different locations throughout the state. But the long-term average, the 71-year average, is a 4.3 degree Fahrenheit increase in temperature in the state of Alaska. That is 0.06 of a degree Fahrenheit per year. Now, you've heard, or if you paid attention to the concerns about global climate change, there's a goal that the Intergovernmental Panel on Climate Change has set of trying to keep climate change under 1.5 degrees C. For Alaska, in the last 71 years, we've already warmed 2.39, almost 2.4 degrees C. Substantial warming. Why is this important? Because the glaciers in Alaska, most of which are at elevations below 2,000 meters, below 1.5 miles or so, are rapidly melting, and more than 99% of them are definitively losing large amounts of ice in terms of area, volume, and large amounts of meltwater flowing through Alaskan rivers to the ocean. If you look at just the last 44 years, the amount of warming has actually been 1.5 degrees C in Alaska. And so Alaska and the higher regions, both in the Arctic and the Antarctic, higher geographically in terms of latitude, are experiencing tremendous rates of change. Here's a bar graph showing temperature diversion from a norm. And so if you look at the years, 1940 to the left, 2020 to the right, and you can see that since 1980, far more than half the years have been extremely warmer than norm. And you can see in the last decade, almost every year has been significantly warmer than the long-term norm. And here's a global map showing the same thing. Notice the bright red colors, especially in the northern Canada and Alaska and all of Siberia, most of Eastern Europe. Antarctica is shown as being in an area where there's not enough data to make any real determination. But the same impact that we're seeing here, we're seeing in Antarctica, and it's having dramatic melting impacts on the perimeter of Antarctica. So quickly, some numbers about glaciers. So temperature, warm ice, and warm ice is something that is actually real. It's not just a make-believe phrase. Warm ice is ice that's very close to the melting point. So most temperate glaciers in summer, surface of ice in Alaska is a fraction of a degree below 32 degrees Fahrenheit or 0 degrees. Whereas at the South Pole, in the middle of South Pole summer, the ice may be minus 50 degrees Fahrenheit. So dramatically colder than what we're seeing by order of magnitude. This is the number of glaciers that the Randolph Index has identified globally, about 198,000 glaciers. This does not include the ice sheets or smaller, less than a half a square kilometer bodies of ice that are referred to as glacierettes. You include that number, you're looking at a little bit less than 500,000 glaciers. Here's a really interesting analogy. If you had 1,000 drops of water on Earth, where would they be? Well, 972 of them would be in the oceans, 21 would be in glaciers, 6 would be in all the groundwater and soil moisture on Earth, less than 1 in the atmosphere, less than 1 in all lakes and rivers, and less than 1 in all living things. So 21 drops represents 75% approximately of all the fresh water on Earth is tied up in glacier ice. So 2.8% of all the water is fresh water. Of that, 3/4 is glacier ice. So glacier ice is the second largest reservoir of water on Earth beyond the oceans. If we take this analogy a little bit further and assume there are only 1,000 ice crystals representing all the glacier ice on Earth, 914 of them would be in Antarctica, 79 would be in Greenland, about 4 in North America, with about 1 of those in Alaska, the majority of them are in Canada, about 2 in Asia, and less than 1 everywhere else on Earth. So Alaska is significant, but when you look at where 99% essentially of all the water is, it's in the polar ice sheets, 99.3%. So less than 1% of all of Earth's glacier ice is in temperate glaciers, temperate ice caps, temperate ice fields, and mountain glaciers. And this map shows the distribution of glacier ice on Earth. So you can see Greenland and Antarctica are where most of it's located. The Little Ice Age was a period of time between about 1250 AD and 1900 AD, when glaciers on Earth expanded on all continents but Australia. And there were probably 4 degree Fahrenheit decrease in temperature compared to 20th century temperatures. The coldest part of the Little Ice Age was during the second half of the 17th century, in the early 18th century. Many glaciers in Alaska began advancing somewhere between 12 and 1400 AD. Many of them started to retreat as early as around 1800. Most of the glaciers in the Juneau area were retreating by 1750. Here's where glaciers in Alaska are located. Surprisingly, of the 14 different areas where glaciers exist, 12 of them are within a couple hundred kilometers of the Pacific Ocean. So most of Alaska's glacier's ice is along the Gulf of Alaska coast. I mentioned before, more than 99% of all the valley glaciers in Alaska are melting. A few are advancing, which is quite interesting. And one of the glaciers that we studied this past summer in the Kenai Fjords, the Holgate Glacier, started advancing about 5 years ago. And we'll look at that at the latter part of this presentation. So let's talk about glacier photography. Bill mentioned that I use photography as a major tool in what I do. And I've been doing this now for more than 50 years. So just some firsts for Alaska. First known photograph of a glacier in Alaska, about 1883. By 1920, more than 400 Alaskan glaciers were photographed. By 1929, almost all the glaciers in southeastern Alaska were photographed from the air. By 1960, all glaciers in Alaska were photographed. Beginning in the early 1960s, space-based imaging, the Landsat satellite, and now probably 50 other types of satellites, began imaging Alaska's glaciers. And so Landsat has covered all of Alaska's glaciers, probably in some cases repeating the imagery more than 500 times. So this is the first known photograph of an Alaskan glacier. This is near the mouth of Muir Inlet in Glacier Bay. Date approximately 1883. Commercial photographer named LaRoche from Seattle. There may have been others, but this is the one that is documented. And this is one of the first aerial photographs made by a US Navy, US Geological Survey joint expedition in 2 years, 1926 and 1929. They had 4 open cockpit biplanes with 2 cameras, one through a hole in the bottom of the fuselage and one being held by the co-pilot in the back seat in the plane and resting it on the gunnels. And so this is an area in just east of Juneau. This is the Twin Glaciers. It's the Juneau ice field. This image is the 1926 image from the expedition. The next 2 images are a photograph on the right that I took in 2013 and a satellite image of the same place, showing that you can compare images from many different sources to make determinations of how the landscape is changing. The map on the left shows all of the center points where satellite images collected by Landsat have glaciers within the fields of view. And this, as I've mentioned, the Landsat satellite has been imaging Alaska since 1972. This is the 50th anniversary. Let me show you 4 Landsat images of the Columbia Glacier. You can see how important Landsat is as a tool for documenting change. This is 1986. The glacier first started to retreat around 1980. And so there's an arcuate ridge at the very bottom of the picture. That's the end moraine where this Columbia Glacier terminus sat in 1980. By 1986, it retreated a kilometer or so. So we're looking at ice all the way down to just above the end moraine. 1986, 1995, 2008, and then 2011. So the glacier has retreated somewhere in the order of 7 or 8 kilometers in the period from the early 1980s to 2010, 2012. It continues to retreat. So I'm going to show you some of the things you can determine from a single photograph. This is the terminus or part of the terminus of the Malaspina Glacier. And what you're looking at here is stagnant ice with a forest growing on it where some of the trees are more than 200 years old. And if you notice, the roots of the trees are sitting directly on the ice surface. And as the ice melts, the trees slough off and fall down the slope here on the side or directly into the lagoon. The Pacific Ocean is immediately behind from where I took this picture. So we're less than 100 meters from the coast. This is the terminus of the Bering Glacier during one of its surges about 10 years ago. And if you notice, there are 2 individuals in the middle of the foreground. The one closest to the camera is me. And so you're looking at a wall of ice here that's probably 150 feet high, about 50 meters high. And this was part of the advance of Bering Glacier, a non-climatic driven event. This is Lituya Bay, part of Glacier Bay National Park, but there are a number of interesting things here. This bare surface in the right of center is where a giant landslide took place in 1954. At that point in time, this was all open water. And so the rocks, more than 1 million cubic meters of rock, fell into the fjord, splashed the water up to this point, 1,754 feet above sea level, washed all the vegetation out and preceded a 300-foot high wave out to the mouth of the bay. This line here is the top of the lateral moraine from the glacier that filled Lituya Bay in the 14th century. So this glacier, Lituya Glacier, and another glacier on the other side, North Crillon Glacier, had coalesced and were hundreds of meters higher than they are presently. And in fact, this glacier had retreated in 1800 when La Perouse visited this bay, and the ice terminus was sitting all the way over here. So dramatic changes that can be recorded in a single photograph, and with a little bit of information, you can interpret it and learn quite a bit about change. Here's a glacier in the Granite Range, part of the edge of the Wrangell Mountains. And here's the ice. You can see the snow line here. Here's the lateral moraine on both sides. Notice here's vegetation. Here's where the end moraine was at the end of the Little Ice Age. So this glacier, and here's the terminus today, this glacier has retreated about 1.5 kilometers in the last 200 or so years, has thinned dramatically, and is continuing to rapidly retreat. And vegetation is quickly forming on the floor of the valley and moving up glacier, up valley, occupying the land that's been abandoned by the ice. So Bill mentioned repeat photography. Here's an example of repeat photography. This is a photo that Gilbert took during the Harriman expedition in Glacier Bay in 1899. And I took a picture from the same location about 105 years later. And so by combining the images, you end up with this kind of a picture. And so I'll do that one more time. This is what it looked like in 1899. This is what it looks like in 2003. Looks the same today. In fact, I was there about 4 years ago, a little bit more vegetation, but the ice had completely disappeared from the field of view. So I'll show you a number of examples of this repeat photography technique and talk about what the pairs of images, or in some cases, triplets of images show. So we'll start with two examples from Nellie Wan Glacier in Prince William Sound. This is 1909. This is what Nellie Wan Glacier looked like. This is a photograph by U.S. Grant, who is an extremely important individual for the Kenai Fords area. And in 1909, he photographed all the glaciers in Kenai Fords as well. We'll talk about that shortly. So 1909, whoops, 2011, 1909, 2011. You can see the changes here. 102 years, almost total disappearance of the glacier ice. This is a more recent photo, same glacier, Nellie Wan Glacier, 1957. And look at the dramatic changes that have occurred. 1957, 2011. So we've gone from a marine embayment in 1957 to a marsh that's been filled in, mature spruce trees, and dense reddish flowers off in the distance.
Dr. Molnia?
Yes, ma'am.
I'm sorry to interrupt again, but we have lost your screen share image. There we go.
Did you see the pairs of images?
No.
Okay, so this was the first Kenai Nellie Wan, I'm sorry, first Nellie Wan Glacier pair. Let me go back. So 1909, 2011. There's the pair, 102 years. 1957, 2011. And so the 1909 photograph was taken from this orange star looking across like this, and the 1957 image was taken from this yellow star looking this way. Columbia Glacier, 1931, same location in 2011. Plateau Glacier in Glacier Bay. This is Wachusett Inlet, 1961. Notice the two people standing here on the bluff. This is glacier ice, open water. Same location in 2003. The vegetation was so dense that my two field assistants over here in their red, orange float coats could not make their way up onto the bluff. 42 years. Look how rapidly the vegetation gets established. Muir Glacier, Coast Mountains. 1886 photograph. Notice the fur muff and the bustle, the top hat, big box camera. Notice this point of land here and here, because this is what we're looking at in 2005. So in 129 years, this Muir Glacier totally disappeared from the field of view. In fact, it's retreated something on the order of about 25 miles to the north. Another example of Muir Glacier, 1895, unknown photographer. Notice the point of land on the left-hand side. Same location. Again, the glacier is completely out of the field of view. Another example, this is a photograph, and I apologize, I have the wrong date here. This is 1941, not 81. I thought I had changed that. And no vegetation to be seen anywhere, bare bedrock, no soil. Same location, I revisited in 2004. Let me go back so you can see the change. 1941, beg your pardon, 2004, 63 years. In 63 years, we went from a bare rock surface to a forest with alder, willow, a little bit of spruce and cottonwood. Rapid evolution of what's now almost a mature forest, and vegetation growing on the flanks of the mountain opposite. The thickness of ice that disappeared here was approximately 600 meters, about 2,300 feet. And so in 1941, when that first photograph was taken, this is the point where the photo was taken from. The ice sat right here. In 1950, it was about here, and it's now 6 miles further up the fjord to the left. Another example, this is an interesting triplet of images. I took all three pictures. The first one in 1976, when the terminus of Muir Glacier was sitting very close to this exposure of rock. There was so much calving and splash waves that this rock was wet enough for marine algae to take hold and survive up here. In 2003, the glacier is completely gone from the field of view. The first alder has come in, but obviously the algae has died off. There is no splash activity, and here we are several meters above high tide. This is 2003, and this is 2019. Again, the rocks continue to weather, but now look at the variety of different types of grasses and shrubs that have gotten established. So here we are looking at 27 years between the first two pictures and 16 years between the second and third. Another interesting pair of images, 1978, terminus of Muir Glacier. I did not know when I took this picture that there was a 4,000 plus foot mountain sitting right there, but it was completely hidden by the height of the glacier, and I thought those were just clouds. But if you look closely, you can see the little depression in the summit and the arête ridges that you see in the 2003 photograph. So we looked at Muir Glacier in 1941. It was up here. 1950, it was off the image to the left. And since then, it's retreated. This is where it was 2004, 2015, and a little bit further back in 2019. So now I'd like to finish by talking about the MV Endeavour Kenai Mountain Fjords expedition of last August. So as Bill mentioned, I brought a couple of my colleagues with me. And since we got off the boat, actually wrote a paper that was published in a European geodesy journal called Documenting 20th and 21st Century Glacier Change, Landscape Evolution with Maps and Land, Aerial, and Space-Based Geospatial Imagery in Alaska's Kenai Mountains. And it describes in great detail what we found. The glaciers that we discovered were retreating very rapidly in most cases, and the one exception, the Holgate Glacier, which, as I mentioned before, began advancing about 5 years ago. So here's the area that we looked at: Resurrection Bay with Bear Glacier, Ayalik Bay with Ayalik, Pedersen, and Holgate Glaciers, Northwestern Fjord with Northwestern Glacier. We also went into McCarty Fjord, but the weather didn't permit us to do much useful photography. But this is the area located south of Anchorage, and it's a really dramatic area of rapidly changing glaciers, as you'll see. So this is a Landsat image showing glaciers I mentioned. This is an image that was actually collected while we were on the boat in the fjord. And what I want to point out to you is that the fjords that are on the, or in the mountains, in all cases connect to older, much larger sea valleys and marine fjords that were created during the Pleistocene. So this is Resurrection Bay up here, but this is the extension of it, going way into the continental shelf of the Gulf of Alaska. Same thing with McCarty Fjord. It continues out. And you can see the yellow, orange, or the deeper depressions, and you can see the sediment aprons around each of these massive Piedmont lobes that would have been created during the Pleistocene. So these two images, if you look at them closely, you can see significant changes in Bear Glacier, significant changes in Pedersen Glacier, and small changes in some of the others. But these are 48 years apart. So let's look at Bear Glacier in Resurrection Bay. And what you see here are 6 aerial photographs. The one in the upper left was taken by a colleague of mine, Austin Post, in 1961. The other 5 are pictures that I've taken. And you can see that after 1961 until about the early part of the 21st century, there wasn't much change. Then the glacier started rapidly retreating. And between 2002 and 2010, it retreated about 6 kilometers. So here you can see the same intervals of time on the Landsat image, but let's take a look at annual changes using Landsat imagery. So 2000, there's still part of the glacier that's almost in contact with its end moraine over here, starts retreating, breaking up, mostly on the west side, on the northeast side, I beg your pardon. And then the west side starts rapidly retreating after 2004, 2005, 2006. By 2007, it's opened up a lake that's about 4 kilometers across. And if we take it back to 2021, when we were there, the terminus would be about here. So a pair, this is from a postcard at the time of 1920s. President Harding visited in 1923. And so we believe the postcard dates from that time period. So 1920s, and then 2006. And everything you see here are icebergs floating in the lake. The glacier is retreated well out of the field of view. Picture from 2006 and a revisit that we did last summer. And so we've gone from the glacier terminus on the right and large icebergs in the lake on the left to smaller icebergs and no view of the glacier at all. Another example, this was the terminus in 2006. And again, it's retreated another 2 or 3 kilometers to the right, 2021. Pedersen Glacier. This glacier retreated in the last, between 2010 and 2021, about 4 kilometers. But here's a 2006 image of it and the same location in 2021. Little Hole Gate, a 1990 photograph from the Park Service, and the same location in 2021. This is a really interesting glacier called Little Hole Gate. And notice the rock behind me. I'm pointing to a stream channel that was dumping a significant amount of water in 2005. We went back, and this is the same rock and no glacier. Here's the wetted bedrock surface. The ice margin is over here. So between 2005 and 2021, 16 years, we lost all of the ice that was on the valley floor and all of the ice on the slope. And you can see just the edge of the terminus here. This is a 1909 photograph by Grant. 2004. 2021. It's a triplet. Now let's look at 4 images from 1909, 2004, 2011, 2016. In each of these, you can see Little Hole Gate and Hole Gate, and they are slowly retreating. Little Hole Gate going up the valley wall, Hole Gate disappearing pretty much from view. 2016. And here's the picture we took in 2021. Little Holgate continues to climb the valley wall, but Holgate Glacier has advanced significantly. Go back and look at where it was 5 years ago, 5 years before our August expedition last year. And then here it is re-advancing, and it's advanced about 300 meters in the time period of just about 6 years. So really an anomaly. I can come up with a plausible explanation of why it advanced, but this is happening very infrequently throughout Alaska. About a decade ago, there were probably a dozen glaciers that were advancing or at least not retreating. Now the number is less than one handful. So I'm going to stop there and be happy to take your questions. And I hope you found this informative. I'm available by email if you'd like to ask further questions, but let's see if I can answer your questions now. So I thank you very much.
Thank you so much, Dr. Molnia. We do have a lot of questions. So I'm going to begin with, well, before I get into questions, I would just like to let folks know that you can continue to submit questions into the Q&A section if you have questions for either Dr. Molnia or for Bill Urschel. And if you aren't able to stay with us through Q&A, it's going to be fascinating, but just in case you have to drop off early, I want to thank you for taking the time to join us. And we'd love to have your feedback on the webinar. Visit our website, alaskaendeavour.org, and connect with us on Facebook. Okay, so now to the questions. From Clarence, we have a question. Do you somehow get these photographic comparisons to the public and the powers that be?
I try. I share my images with something called the National Snow and Ice Data Center, which has a large repository of photography that's free to anyone who wants to access it. I've had some of my pairs used by the media in a couple of cases more than several hundred times. I make them available at professional science meetings, and I give lectures whenever I have the opportunity, but there's not a simple channel to make this information publicly available, but it's all out there in the public domain as often as I can get it.
Okay, and then Ray in Anchorage asks, it looks like the glacier in Lituya Bay is advancing, not retreating in a warming trend. Why is that?
Lituya Bay's glaciers are really unusual. As I showed in that picture, they were a couple hundred meters thicker based on the height of the moraine in the 14th and 15th centuries. And then they retreated right in the middle of the Little Ice Age from where they were at the mouth of Lituya Bay, almost 10 kilometers into the arms of the fjord at the head of the bay. They began advancing sometime around 1800 AD, and they advanced for about 200 years. And in the last decade, they have begun to retreat. So they are out of sync with what you would expect in a warming environment. But what happens with glaciers today is a reflection of what happened in terms of accumulation of snow 50, 100, or in some cases, several hundred years ago. So it's a combination of where they sit in terms of their orientation, the heights of their accumulation areas, the width of their channels, the amount of sunlight they receive. But you're correct. This glacier is asynchronous. It's not behaving the way you would expect a normal glacier to act based on what weather and climate we're doing. And remember, there are 27,000 glaciers or so in Alaska. There are a handful that behave unusually, and all of them have their own unique circumstances. But yes, this one is doing things that would not be expected. Next question, please.
Okay.
Oh, I'm sorry, but however, it did stop. It's now going back into a retreat phase. Sorry, go ahead. Next question, please.
Okay. Hang on while I share my screen again. Sorry about that. So another question is, why should I care about the consequences of climate change? Aren't some areas going to be better than they have been in past centuries?
It depends on where you are and who you are. If you live in a coastal area like South Florida and sea level comes up another 5 or 6 inches, you will be flooded so frequently that it's not probably worth your while to continue living within a kilometer or two of the coastal zone. If you're living in a place where the temperatures are 30 and 40 degrees below zero in winter, maybe a 10-degree warming, which is what some parts of Alaska have experienced, will make it much more habitable. So yes, if you're looking at it from an individual perspective, there are going to be winners and losers. But if you look at it from a global perspective, ecosystems are going to be impacted. As I said, huge numbers of major parts of our national infrastructure, not only ours, but global infrastructure, are going to be negatively impacted. There's going to be significant changes in ocean circulation. Many species of fish that are in habitats that are reasonable for them and they survive today are going to lose. It's going to get too warm, or it's going to get too acidic in the oceans. And we're going to see total revamping of ecosystems as we know them. We're already seeing that with coral reefs, where many of them are dying very quickly because of the warming of the water. So even though things are going to be warmer, it doesn't necessarily mean it's going to be better for everything.
And another question, do we have the technology to counteract the consequences of climate change?
We have a lot of theories on how we can do major geoengineering, but nothing that has been successfully conducted. And the reality is, as long as we are continuing to burn as much fossil fuel as we do and continue to pollute with other types of chemicals, we're going to have a continuing negative impact on our global ecosystem as we know it.
Next question is, what was the Fiducials program and why was it important to the study of climate change?
You have to put this in context. The Fiducials program evolved in the early 1990s. At that point in time, the public had access to Landsat as probably the only satellite that they could use for understanding what was happening to the Earth's surface. And Landsat had a resolution of 30 meters. The Fiducials have a resolution of 1 meter. And they were based on using assets collected by the intelligence community to look at rapidly changing environmentally sensitive areas of the Earth's surface. And the idea was that the data would be classified and kept classified for a number of years until the technology was no longer considered to be critical. But what happened was that because the imagery was being analyzed and scientists who were using it, cleared scientists who had security clearances were using it, they recognized how important some of the changes they were observing actually were. And so an effort was made to find a way of making some of this high resolution imagery available to the public at a resolution where you could clearly see how the Earth was changing. Since the early 1990s, there are a number of commercial satellites that have developed and have been collecting imagery that is comparable to the resolution of the Fiducials imagery that was released. But they all are for profit. There's no free information that you can get that comes anywhere close to the resolution of the Fiducial imagery. So it showed things that we didn't know were happening, and it was made public so it could be understood by the greater populace how important these changes, how important these things that were being observed could be to impacting our lifestyles and our way of living.
Okay, thanks. And here's a question and comment from David Lee. He says he's been using images of near glacier retreat from your 2007 paper for teaching at UCSB ever since, and he's going to use them again for his lecture on Monday. And he says, thank you. And he's asking if you could give your perspective now as to how much of the observed retreat is due to global warming versus warming as the Little Ice Age subsided.
That's a really good question, because that's something that's being debated and has been debated by the science community for the last 20 or so years, as to this warming that we saw accelerate around 1980 Was that all human caused, or were there other factors? And the simple answer is many of the models suggest that most of it is directly being impacted by human activity. To be honest, my part of the science is studying the glaciers and looking at the results of the temperature that is changing, as opposed to understanding why the temperature is changing. So all I can do is repeat what I've read. And most of what I see that is credible suggests that the human impact is far more significant than whatever residual warming trend might have been occurring post-low ice age.
Another question is, what's special about the glaciers in Glacier Bay? Why is your expedition there this year important?
For several reasons. Glacier Bay has probably the longest photographic record of any place in Alaska where glaciers exist. And there was not only tourism in the 1880s, but a scientific expedition by a geologist named Harry Reid in 1890 and 1892. And he took about 600 photographs, which are available to the public through the National Snow and Ice Data Center. And so I have a number of his photos that I'd love to go back and try to duplicate. The other thing that makes Glacier Bay important is that it was observed at the time of Vancouver, so in the 1780s, and it had already begun retreating from its end moraine. And in the time period from Vancouver to the present, the ice in Glacier Bay has retreated as much as 60 miles. And so based on the magnitude of glacier retreat and the ever-changing landscape, it's an important place to visit every several years to update the record.
Thank you. And Kristen asks, exactly how disturbing is the speed of glacial retreat? If they've been retreating since 1850, what effects does the increased rate of retreat have?
Let me think about that, because when you say what does the rate have, it continues to, well, it's exposing more previously unexposed bedrock that has been under ice for several thousand years in some cases, and exposing new areas that are rapidly being colonized by adjacent terrestrial ecosystems. So, the seeds blow in, they get started quickly, as we saw. As soon as you start getting something for insects to pollinate, the insects move in after the pollen, or to eat some of the vegetation. Then the predators come in, and as soon as you get small mammals in, you get larger mammals, and very quickly you get the birth of a what turns out to be a very complex ecosystem in an extremely short period of time. And so with Glacier Bay's continuous retreat of its ice, you can see over the last 200 plus years, this migration of a new ecosystem from the mouth of the bay, up the bay, and into the individual fjords that are being exposed by the retreat of some of the tributary glaciers. And now that they're being exposed more rapidly, you can follow this rapid succession of colonization by all of these both plant and animal species.
And a question from David, can you discuss the difference in response of tidal versus mountain glaciers in Alaska?
Yeah, so you have to put Alaska in perspective. It has ice that goes from perhaps 400 or 500 meters below sea level in some of the fjords to the summit of Denali. So you've got glaciers that are temperate, tidal glaciers, and you've got valley glaciers, and then you've got colder valley glaciers going up the sides of the mountains. About 100 years ago, there were probably 150 plus or minus tidewater glaciers in Alaska. With warming and retreat, I don't know the exact number now, but it's probably well under 30. Fewer and fewer. In fact, when I first went to Glacier Bay in 1974, there were probably a dozen fairly attractive, healthy tidewater glaciers. I think the current number is 3 or 4. Same thing in Prince William Sound, not as rapidly a loss, but Many glaciers that had been tidewater are retreating back onto land and out of the water completely. Many of them are developing sediment bodies in front of them. So the mountain glaciers lose ice only by melting. The tidewater glaciers lose significance of, have lost significant amounts of ice by calving. And so in some cases, calving may cause the retreat of a glacier to be an order of magnitude more than would have taken place by melting.
Okay, and a question from Robert. If global warming stopped right now, would most of the glaciers in Alaska that are now retreating stop retreating, or would stopping their retreat require the atmosphere to cool down? And if so, by how many degrees?
I can only speculate on that. If we ceased adding new greenhouse gases to the atmosphere and continued where we were, we'd still see a retreat of most of the lower elevation Alaskan glaciers, because we've seen over the last 70 years that 4+ degree Fahrenheit warming, we still have that changing atmospheric circulation. We have changes in precipitation patterns. We have a number of other factors that would not immediately revert by the lack of addition of new warmth, so to speak. So I don't think we would see as rapid a retreat in many cases, but the temperature at sea level has increased. If you look at those first order weather stations, has increased in some places 3 to 4 degrees Fahrenheit, not as much as some of the more northern latitudes, but it's still a significant temperature increase from where we were in the 1950s. And so if that's going to be the mean annual temperature for the future, we will still see an increase in melting, or a continuation of the increased melting.
And let's see, Chris asks, what's worse, increased glacier melt or permafrost melting?
They're two different things. The glacier melt, if you're talking about ice sheets, is probably far worse, because that's where most of the sea level rise is going to come from. The melting of permafrost is releasing large amounts of methane and other greenhouse gases that have been frozen for thousands of years. The melting of the permafrost is also, in many places, a major factor in undermining existing infrastructure. Where the glaciers are located, especially in Alaska, it doesn't have much of an impact on any existing infrastructure. So they're both important, but the permafrost, in terms of climate change, may have a more significant impact.
And let's see, we've got a great question here. How did you become interested in glaciers, Dr. Molnia?
So, interesting story. I grew up on the East Coast. And when I was in 6th grade, my parents bought a house that when we moved in had no grass, just had a bare earth lawn. And the lawn was made up of sand and gravel. And there were probably 150 different rock types that I could pick up as pebbles in my front yard. And when I asked people where all of these amazing different rocks came from, the response I got was the glaciers brought them. And so my first opportunity to learn what a glacier was when I was a senior in high school. I took earth science and had an opportunity in college to actually not only study glaciers, but to go to Antarctica and Alaska. And that started more than 50 years of working in Alaska, and 4 trips to, or three research trips to Antarctica over the years. So I have been sort of very fortunate to have a curiosity that's led to a lifelong profession.
Thank you, Dr. Molnia. We have several more questions, but I think what we might do is include the answers to those questions on the website after we post the recording of this excellent webinar at alaskaendeavour.org. And for those of you who asked those great questions, thank you so much. We'll get them answered on the website when the video is posted. And I want to thank you so much, Dr. Molnia, and I want to thank all of you for joining us. And thanks also to our sponsor, morethanscientists.org. I hope you leave inspired to get more involved. I hope you stay connected with this community of science, exploration, and conservation at Alaska Endeavour. Join us for our next online event. Sign up at alaskaendeavour.org or follow us on Facebook to stay in touch. Goodbye.
Bye-bye.